let's start coding.
Welcome back to the coding tutorial on feed-forward neural networks. In this tutorial, we will look at gates and how to code them in Python, and we will code our very simple implementation of a feed-forward neural network with a single neuron. So let's start off with the gates. I've pre-coded everything just to make sure that everything works so that y'all don't have to sit around waiting for me to just type the code up. I'm using two libraries here. I'm using the math library and the random library. So, use those two libraries. It makes our lives easier. And we're going to be looking at different types of operands. So here's a single input operand. An example of these is the negation operand and the exponentiation operand. Here's how our entire design is going to be. We're going to be using classes in Python to define these input operands. So each wire, each input, has a value and a derivative. And then it has an operand that's associated with that. So that operand would be exponentiation or negation in this case. And then an output as well. And so the value goes from the left to the right while the derivative propagates from the right to the left. And you'll see that as we code the thing. Here's for a 2-input operand. This should make sense. And then we can extrapolate for more gates. You can add more input gates here. You have value of x3 if you wanted to. So let's start off with the exponentiation gate. It's a single gate. It takes an input, it exponentiates that value, and it produces an output. We're going to define a class called exponentiate here and have an initiation function with x1 being our input. So we've defined x1 to be our input, and our output we're going to say is going to be y1 as we've defined here. We're going to have derivative values for both dx1, dy1. Let's activate, meaning going from the left to the right. We're going to exponentiate x1. And that's what we do, math.exp, and we set it equal to the output, this output right here. That's what happens when we activate it. That's the same thing as we can see here in the first slide, the gates. A exponentiates, and then it goes to C. So e to the A is equal to C. Kind of basically what we did, A is x1, C is y1. When we backpropagate, we're essentially doing the derivative gates. We're going to take this value, dc right here, and we're going to multiply it by e to the x1. And so that's what we do. We have c, the dc, which we've defined to be dy1, right? And then we multiply that by math exp x1, and we set that equal to dx1, which is what this output is right here. And so that's how we activate and backpropagate. I've done the same thing for the negation gate. As you can see, the initiation is exactly the same. For the activation, this is what we do. Multiply by -1, because that's what the negation gate does. It multiplies A, our input, by -1, and it sets it equal to our output. And for backpropagation, it's the derivative, and so that's exactly what we do here. The derivative is the same in this case, so that's how we set the backpropagation. Addition gate now gets interesting because there are two inputs. So we've defined two inputs here. We have an output, we have our derivative values here, and then we state, all right, how do we activate it? Well, we just add the two inputs together, right? In our gates, it says A plus B is equal to C. And so that's what we do. A is x1, B is x2. A plus B is equal to C, which is y1 right there. So we just add the inputs together, set it equal to the output. For the backpropagation, what we do is we do this exact same thing for these gates, right? We have the derivative with partial derivative with respect to A, partial derivative with respect to B. That's just dc, which is the derivative of y1, so we just set that equal right there. And then what we get is essentially the same thing that is defined in our function. So that is how that works. The subtraction gate, the same thing. I look at this gate, and I say, all right, the subtraction gate negates for that derivative. It just subtracts A minus B for the activation. So activation, subtract, we negate that gate for the backpropagation derivative. Multiplication, same thing. So you can take a look at this. I'll post a link to the GitHub page down below. Take a look at this, and you should understand how I'm defining the gates. Same thing for the division gate right here, right? And so that's how we backpropagate the division gate as well, just by using these functions that we did in these slides right here. Sigmoid gate. So this is interesting because we're using the other gates. Let's go to the sigmoid function. We're using the other gates to create the sigmoid gate. So I'm going to show you how to essentially do that. So we have one input, as you can see. A is our input into the sigmoid activation function. And we have one output. Same thing in our sigmoid activation function, C. So using 4 gates that we've defined in our activation function, we have the negate, we have the exponentiate, we have the add, and we have the divide. Take a look at this. Negate, right here. Exponentiate, add, divide. Negate, exponentiate, add, divide. And we have to activate it after each time because we're saying, all right, A, we have to activate this gate to let A through here. Now it's negative A, so we have to activate that. And then now exponentiation gate, we have to activate it to let negative A go through, so you get e to the negative A, etc., all the way down the line. And that's exactly what we did here until we get the end value. Take a look at that and see if that makes sense. I'm going to go over that a little slower so you understand it. We have a negate gate. A is our input. We negate A. Here, x1 is our input, so we negate x1. We have to activate it to let that value pass through this gate into this wire right here. From this wire, we want it to go to the other side of the exponentiation gate. And we do that by activating the exponentiation gate, which is what we do here. We set that previous value, right? We set the previous output value. Y1 is the output value of the negate gate. We set that previous output value as the input of the exponentiation gate, and then we activate it. And then what that does is it brings it over to this side right here, to this wire. And then we have 1 and then this value of that wire right there. And we set that 1 and this wire's value as the input of the addition function. 1 and the output of the previous gate. We activate it so they're added together and it's set to this wire right here. We do the same thing for the division gate. 1, right? 1 here, activate it. And then now it goes to the output, and that's the output that we have for C. And so we set that equal to the output for C. When we backpropagate it, that's finding the derivative, right? We just do the exact same thing. We have a sigmoid activation function right here. We have dp, our derivative input. That's dy1 right there. That's our dp right there. We set it equal to the division function's input for the derivative. All right, we backpropagate it. We essentially throw away dx1, which is the first input right here, because we set that to 0. And then we set dx2 as the input to the addition gate right here. And then next, we throw away this value because it's a constant, so you don't see dx1 right there. You only see dx2, and you set that as the input of the exponentiation gate that we have here. And then we keep doing that, and then we have the negation gate. We backpropagate again, so we open up that gate again and backpropagate, so we set all these wired values. And then at the end, we have the derivative of the sigmoid activation function. And doing this, we can create really complicated neural networks. So that's how essentially we've created our basic gates. And then for our addition gate, as we talked about, we're going to be using 2 addition gates to create a 3-way addition gate. So we have 3 inputs to our addition, right? 1, 2, 3, x1, x2, x3, right here. Those are our inputs. We have 1 output right here. And then we have our derivatives for our values that we're interested in. So we have our first addition gate that takes in x1 and x2. First addition gate that takes in x1 and x2. And then we activate it so that this wire right here is set to the value of x1 plus x2. Right? And then we set a second addition gate right here. Right? That's a second addition gate. And then we activate that. So that's the output of the first addition gate. And then the input x3, output of the first addition gate, input x3. And then we activate that. And then we get the output value right there. Backpropagation, same thing, looking at these diagrams. If you make these diagrams, it makes it very easy for you to create any sort of neural network. So we set it equal to dc, right? dc is just dy1. We can define that later as the addition. We backpropagate that to set the wire values, both here. Right? So we have backpropagated and set those wire values, the dx1 and dx2. And then we have the dx2 of the first addition gate be just x3's derivative. And so that's exactly what we have here. 4-way addition gate. I'm not going to explain this too much, but you get the point, right? If you have four additions, then you do that. And that's it. And then now we're going to get to the design of our first neural network. But please take a look at that video and understand how we essentially did those gates, because that's the key for our neural networks coming forward in the next video. Thank you.